presentation, which is volumes and densities of 40 asteroids. How am I going time-wise? Okay. This is a presentation I put together earlier this year for New Zealand, but it's based on work which was done by Joseph Durek's group in Czechoslovakia and, well, in Europe, where they've used, they've attempted to determine the volume and the bulk density of 40 asteroids, and they've used a thing called atom shape modelling, which is an enhancement of the shape modelling that they use with the DAMIT system. All the regional coordinators for IOTA are included as joint authors of this paper, which was published in Astronomy and Astrophysics. This is just a manuscript. It was published earlier this year from memory. But as an appendix or at the end of the paper, it lists all the asteroidal occultation results which were used, including the names of all the observers. So chances are a whole heap of people, if you're listening in or at the conference, you'll find your name included in this paper. And I thought I should talk about it because it's the end results are interesting, but it is in effect an illustration of, if you like, the end game of what we're doing with our asteroidal occultations, because it's combining the size that we get out of asteroidal occultations with the shape that you get from the light curve inversion with the mass that you get from astrometry with mutual perturbations of the asteroids to actually derive the density of the asteroid. And when we get to the end of this, you'll see some interesting results. So next slide. And actually, if you need, you can bear with me a second, so I bring up this presentation myself on my own screen so I know what I'm actually talking about. Okay. So, why diameter is important? Primary characteristic. We know that several satellite missions have measured the diameters for thousands of asteroids. You got IRIS in 92, Akari 2011, and WISE 2013. And then you've got a whole heap of other efforts that have been made over the years to measure diameters. And when you're planning occultation observations, it's important to know how big the thing is, whether it's 300 kilometres or 30 kilometres or 3 kilometres. And I should add in here, in Europe, they've been successfully getting occultations of asteroids which are smaller than 10 kilometres. Usually they're always just single chords, but they're actually stretching things out at the small end. Next slide. If you know the density of the asteroid, then you know a fair bit about what's going on in the asteroid. And the thesis is that asteroids are, they're analogues, they're related to the building blocks of the solar system. And if you understand the density and internal structure of asteroids, then that could tell you a lot about how the solar system was formed and how things evolved. So in the big picture issue, working out the density of asteroids is an important tool, important objective of the exercise. Now, if you're going to measure density, you've got to know the mass and volume of the asteroid. Next slide. So the challenge, density is mass on volume. So we need to get reliable mass measurements and reliable volume measurements. A challenge, and this is going to be the long-term restraint, is mass measurements are only available for a relatively small number of asteroids because it's, you get the measurement by looking at how one asteroid affects the orbit of another asteroid. So you need large asteroids impacting on smaller asteroids and looking at, if you know the mass of a large asteroid, and you can work out the mass of the small asteroid if it moves sufficiently close to it. That's in the long term going to be the biggest challenge in this area. So mass measurements, limited number there. On the diameter, satellites, IRIS, WISE, ACARI, AccuA, they derive mean diameters from a huge number of asteroids. When you look at the number of asteroids in WISE, it's a huge, huge number. And ACARI is a large number as well. They're infrared mean diameters. They're not a direct measurement of the diameter. They're looking at, they measure the brightness in two infrared wavelengths, and it's the ratio of the brightness in those wavelengths that they use to get the diameter. I can't remember the exact details of how they do it. As I showed in that previous presentation, the diameters from the three satellites, sometimes they're fully consistent and sometimes they're quite variable. And in fact, let's see, you'll find that there is no one satellite which is preferable to the other in terms of giving the most reliable diameter. You'll find instances where any one of those satellites will give the best diameter, and the other two, the diameters are clearly not right. Next slide. Mass determinations, orbit deflections. Gaia will expect to increase the number of asteroids with reliable, if you can call better than 20%, reliable mass determination, but that's the type of figures, uncertainties we're talking about for a reliable mass, 20%. On the other hand, if you've got a binary asteroid, and you measure the component, the orbital characteristics of the binary asteroid, then you can accurately determine the masses from the system dynamics. Next slide. Volume of the asteroid. We've got mean diameters of the asteroid. There's an interesting issue that comes up around mean diameter. A mean diameter is simply the diameter of a sphere that is in some manner equal to the asteroid. Now, if you're interested in the density of the asteroid, what you want is a sphere which has the same volume as the asteroid. But when you're looking at light reflections, and I emphasise again, The satellites are using infrared reflection from the surface of the asteroid in 2 different wavelengths. Light reflection measurements are inherently provide the surface equivalent sphere, so a sphere that has the same surface as the asteroid. Next slide. For a sphere, the surface equivalent diameter is the same as the volume equivalent diameter. For a cube, which is rather extreme, the surface equivalent diameter is 12% larger than the volume equivalent diameter. That is, if you take a sphere that's got the same volume as a cube and a sphere that has the same surface area as the cube, that second sphere is 12% larger than the first sphere. If you've got a slightly elongated cube, and the example I've got there, the sides are 4 by 6.8, 4 by 6 by 8. The difference in diameters is 14%. And if you do an asteroid like Cleopatra, where the diameters or the radii of diameter and crudely is 217 by 94 by 94, approximate that with a cube, the difference is 16%. So when you talk about what is the mean diameter of an asteroid, you probably all think about, oh yeah, it's a mean diameter, it's sort of just an average in some manner. It's in fact rather more complex than that. And next slide. In summarising this, photometric measurements give a mean diameter based on equal surface area. We need a mean diameter based on the volume, and density determinations require knowledge of volume. And when you start looking at irregular shapes, the mean diameter based on equal volume is almost always smaller than that based on equal surface area. And for irregular asteroids, the difference can be more than 15%, which means that we need the method to derive volume equivalent diameters, not surface equivalent diameters. Next slide. Shape of an asteroid. Well, there's a small number of asteroids which have been directly imaged by spacecraft, so you can measure the shape very accurately. You can get direct imaging with very large telescopes. Doesn't happen very often, and the resolution is somewhat limited. Radar imaging, when you get a near-Earth object whizzing past the Earth, they can get very detailed shapes of small asteroids whizzing past the Earth. You can try to work with multiple occultation results by themselves using single event profiles and try to combine them together. And to be candid, that's the approach we thought was where we were heading to in the 70s, 80s and 90s. Let's get our multiple chord occultation observations, and then we'll be able to fit them together, multiple events, and work out the diameter. It's my experience to combine the chords from one occultation result to the other without any further information. It's bloody hard to do. In fact, I haven't seen any situation where you could say, oh yes, we can combine this 1974 set of results with the 1996 ones, with the 2014 ones, and the diameter is this. Our occultation results, in fact, do not enable that to happen with the particular information we have available. We're short on information. Light curve inversion gives the shape of the asteroid. And next slide. And I think it's important to understand exactly what's happening with or how light curve inversion works. All asteroids exhibit light variations, they rotate. The limitation on the light curve inversion technique, it's only possible when there is significant variation in the inclination of the asteroid's axis of rotation as viewed from the Earth. So if the axis of rotation lies in the plane of it lies perpendicular to the plane of the asteroid's orbit, and the orbit is pretty much aligned with the ecliptic, then you don't get variations in the light curve variation in different parts of the orbit. You need to have the light variation differing in different parts of the orbit to do this light curve inversion. The technique, it's a complicated mathematical technique. They models the shape of the asteroid to reproduce the light curves, and in that process they can derive the volume equivalent and surface equivalent diameters comes out of the model. And in fact, earlier this year, the DAMIT system, they expanded the info that was available to include the volume equivalent and surface equivalent diameters. That was for an express request from me for that, so that we could deal with this issue of the mean diameter. Now, there are limitations in the light curve inversion technique, which it's important to understand. All asteroids exhibit variations. Next slide. Limitations are important to understand. It assumes the surface of the asteroid is of uniform albedo. Albedo is reflection. If the surface is not of uniform albedo, the inversion process will result in there being a false bump or dip on the surface of the asteroid. So where we have a where we have a shape model matching to our light curve, our occultation chords, and there's some differences, that could be a difference in the true shape of the asteroid, or it could be an indication that the brightness of the asteroid is different in that area to other areas. For most models, the surface is assumed to be entirely convex. My experience to date is that there's a small number of models where they're modelling concave parts to the asteroid, and generally speaking, I've found that the fit to our occultation chords is not improved. If anything, it's degraded by those models. As I indicated before, there's generally an ambiguity in the orientation of the rotation axis. That gives two shape models. They can fit the data with two shape models, fit the data perfectly. Trouble is, one of them's wrong, and our occultation results eliminate the wrong one. And importantly, the size of the asteroid is completely indeterminate. In this process, there is no difference between an asteroid 1 kilometre diameter and another one 1,000 kilometres diameter. If the shapes are the same, the light curve will have the same shape. and there's nothing in the light curve to distinguish between those two models. Whether it's 1,000 kilometres or 1,000 metres, you cannot distinguish that from the photometry, except from the crude estimate of the asteroids about this size. Next light curve. Next slide. Now, if Ted's laptop was had the right stuff on there, you'd see this asteroid, which is Hertha, rotating. And it's not rotating, but there is an example of it's a fit of the shape models to the light curves and two different orientations of the asteroid, and you get a sense of how the shape appears different when you're looking at it from two different points. Next slide. Here, and you can get this Alpha Dammit system. You can see here the blue dots are the observed light intensities, whereas the red line is the light curve which you get generated by the shape model. So you can see the fit of the shape model to the measured light curve points. I should emphasise here that the measurements of light intensity of these asteroids, most of those observations are done by amateur observers. They're Brian, my person's name slipped my mind. There's a group, Brian Warner. Thanks, Brad. Brian Warner organised a global group of essentially amateur astronomers doing photometry of asteroids, with the objective being to build up a huge database of light curves to fit for the asteroid light curve inversion. Next slide. Now, asteroid occultations gives profile and dimensions to about a kilometre. In this case, the asteroid diameter is about 77 kilometres. Apparent diameter was 0.071 seconds of arc. Resolution about a milliarc second. Gives you a resolution of about 1 kilometre. This is an event from back in 2008. It was one of our early events with Scotty with the multiple station deployments. Very nice profile there. Next slide. That's the best fit to the shape model to those chords. At a broad level, it's a very nice fit. It fits the overall shape quite nicely, but you can see on the far right, the profile is well below the chords, and further northwards from there, you can see the chords give a profile which is narrower than the asteroid. So it's not an ideal fit, but it's a pretty good fit in the scheme of things. Now you can see down the bottom of that plot, there's a scale line of 100 kilometres, but above that there are two scale lines. The top side of it is the volume mean diameter of 78.9 kilometres, and underneath that is the surface mean diameter of 83.5 kilometres. So here's a case, the difference between the volume and surface diameters is 5 kilometres for that asteroid. Next slide. Now, unfortunately, if people get this PowerPoint downloaded later on and look at it at home, this actually is a moving image. You can see how the rotation of the asteroid against this event. This is a worse fit than the previous one, but you can see how rotation can change the fit. And as Brad was indicating, for some of these asteroids, you can consider whether there's a correction to the rotation period that comes out of the best fit. Next slide. So out of this, the best fit for this asteroid, volume equivalent diameter 79 kilometres, surface equivalent 84 kilometres, and then interestingly, the 3 satellites, their mean diameters, Iris 79, which matches our volume equivalent, AccuA 73, that's too small, WISE a little bit small, but hang on, the infrared diameters are surface equivalent, not volume equivalent. So here's an instance where, in fact, all the infrared diameters would seem to be too small. Next slide. Now, it is highly desirable in any exercise to look at multiple occultation fits to an asteroid and not rely upon just one event. These are out of that paper, I think. I'm pretty sure they are. And just show the occultation chords, 2 shape models at different orientations. And I think the Cleopatra one down the bottom right is the one which that I was talking about before. And I think all that shows is the topmost chord in the occultation results, where it was a short one aligned with the other ones. There was something wrong with that chord. Anyway, you need to fit the model to multiple occultations to get the best result. You finish up multiple diameter determinations, and you can do a normal statistical thing for that. Next slide. I've more or less mentioned this earlier. You can compare the measured diameters against those from Iris, AccuA and WISE. This is an exercise I did with a sample of asteroids, very significant sample. You find that well, you can see the figures there, Iris about 1%, AccuA minus 2%, WISE plus 5%. But when you look at the standard deviation, they're all about 8%. So on average, Iris is best on average, but for individual asteroids, Iris and AccuA are equally reliable at 8%, as is WISE actually. And I've had some discussions with people behind NEO-WISE, and for a lot of the asteroids we're dealing with, they have problems with image saturation, and that affects their results. Anyway, doing all this, this paper they've, oh dear, oh me, there's a nice table on there which is not displayed. Oh dear. This is the final slide, which was I'm not sure how we can deal with this. I guess this slide shows the bulk density of asteroids that came out of this paper. Down the bottom you see the various types of asteroids there, but let me just pick out a few from the table. You have to get hold of my original PowerPoint to see the... Oh, someone show a desktop. Can I show a desktop? How do I show a desktop? If somebody can tell me how to show a desktop, then I can show a desktop. Yes, I think people need to look at the PowerPoint because there's some interesting figures in here. I'll start at the densest one. In the determination, asteroid 43 Ariadne has a bulk density of 11 plus or minus 3. So that's a pretty solid asteroid. It's clearly an iron type asteroid. At the other extreme, we have asteroid 85 Io and 386 Saigina with a bulk density of 1.1 or 1.0 plus or minus 0.6. So that's the density of water. So presumably an icy type object. A lot of asteroids there have densities in the 3 to 4 range. Not many up around 6 or 7. 3 to 4 of 7. 165 Lorelei is 7. But mainly in the 2s, 3s and low 4s. Which sort of, that's chondrites, carbonaceous chondrites, and perhaps stony ions. So go to the last slide, which is just any questions, I guess, now. What this is showing is what you could suggest is almost an end game for our exercise, is we're actually contributing to the determination of the composition and structure of an asteroid, of individual asteroids, by combining our occultation results with light curve inversion shape models with astrometry to determine the masses, to actually determine the density of asteroids. Questions? I'm not hearing anything, so I'm not sure what's happening. God. Okay, I've just reconnected my system. It's crashed somewhere. You can see there the table of densities. IO in that second column is IO, and next to it in third column 386 Cygina. Density's down at 1, density of water. Whereas Ariadne 43, very, very dense at 11. Significant uncertainty, but still very dense. Aspasia 409, Aspasia, density of 5. So you get a sense of the type of things which are possible with what we're contributing to.